right, and it is screencasting. Perfect. All right, we're looking at number one. Number one. And with number one, okay. Okay, so if you're checking in because you're leaving, no worries. I just need you to say, I'm done with my work. I'm good. I'm going to go ahead and take off. I'm not going to reply to that because it takes too long for me to take a moment to do that. So, yeah, just go ahead and say, hey, Mr. P, I'm good. I'm done. I'm going to go ahead and work on something else. See you tomorrow, whatever. All right, here we go. Number one. So we're looking in the workbook, number one, and we have this expression just listed here. And this really, we want to see, does this always, right? Does this always equal 4x? So when I'm looking at this, the main things that I want to consider here are Pemdas and combining like terms. Because really what we're going to do, we're not going to spend forever trying to figure out, plugging in random values, trying to figure out if this always works, because always is pretty specific. It always has to work. Okay, that can be kind of tricky for something to always work. Okay, so looking at this PEMDAS, let's label our different. Oh yeah, I got different color pens today. All right, we got multiplication. We got some addition, we got some division. Okay, so if I look at all those things, let's see, what would we do first? We would do multiplication, and 3 times x is 3x, 4 times x is 4x, so we don't have anything to do there. Okay. Now, looking at the next thing, we would do division. And this is something that you may not know, but this too can be divided into both of those terms. When we have a fraction, it's all divided by 2, and we can divide each of a numerator terms and divide it by 2. So watch. 5 over 2 plus 3x over 2, we're seeing, does that equal 4x? Okay. And we can reduce even further. Half of 5 is 2.5. Half of 3x is 1.5x. And we're still seeing, does that always equal this? Okay. Now, we've done all of the combining like terms except for addition. And now we want to see, well, can we add those two numbers? And that's where combining like terms comes in. Okay. Because with combining like terms, remember we had this, we had, 5x, 6x, 16, negative 8, right? And let's see, top, middle, bottom. What does x squared match with? Top, middle, bottom from this column. Middle. Good. Yeah. Perfect. All right, 5x, top, middle, bottom. Which one does that combine to? Good, good, good. And then I'm going to say these two, of course, because they're both constants. Now, in the chat, somebody tell me, what do we look at to know if it's a like term? What do we look at to know it's a like term? Somebody let me know. I'll just go with the first person. What are we looking at? Close. Now, the variable may be involved, but it's a little more specific. It's something connected to the variable. What do we think? How do we know if it's a like term?
Exponent?
Yes, the exponent tells us if it's a like term. Look, second power, like terms. We can combine those. First power, like terms. We can combine those. Constant, we can combine those. Okay, so very close, very close. It's not the coefficient. We're actually looking at the exponents. The exponents tell us what we can match. All right? Okay. Now, looking at this is a constant. This is, right, it's a variable, really. It has a coefficient, but it's a variable, you can even say with coefficient. But it doesn't matter here because we cannot combine constants with variables. Since we cannot combine those, we cannot prove if it is equal to 4x. And in fact, we can say it is not always equal to 4x because we got stuck. If this was 2.5x, then we could combine them and it would equal 4x. But in this case, we did PEMDAS. We tried to combine all of our like terms and we got stuck. If you're stuck, then no. Not always equal. Okay. When you get stuck, you know you're done if you can't do any more and you can't simplify it to answer your question. Okay. All right. So I think in the book that number, or that's pretty similar to the book as well. Or sorry, number 3 in the book. All right, Julio and his sister bought 8 books. So I'm going to write things down that are important. Okay, Julio and his sister bought 8 books, right? Um, and magazines for $1 each. Okay, so both of these are $1 each. All right, somebody's coming in late. No worries. Back. All right, so they're $1 each. Let's see, and then they split the cost. Then split. Okay. The amount of money that Julio spent is represented by, so Julio, this is Julio and his sister. So Julio had 1/2 8 plus M. Okay. Does the number of books purchased affect the value of M? Okay. So let's see if this makes sense. Let's look. 8 books for $1 each. It sounds like that's $8 because they bought 8 books, right? M is the and M magazines. It's the number of magazines. So this is let's see, they're $1 each. So essentially, it's $1 times M, right? $1 times M. So this is going to be magazine amounts. All right, someone else is joining. Perfect. Okay, so looking at this, it makes sense here that Julio would spend half, since they split it. Julio is going to use or spend half of whatever they come up with. So since Julio is spending half, then we know that this here must be the total for all the 8 books and the magazines. Okay. So when I look at this, let's see, what page is it on? Is that what this is saying? Yeah, this is in the book. It's page U114. Yeah. Okay. So our final question for number 3 is, does the number of books purchased affect the value of M? All right, let's see. We are adding these together, right? We're adding them together. So if I had 20 books, it would be $20. $1 a magazine, the number of magazines times the dollar. Now, would it matter that the books cost $8 and the magazine costs a separate, $1 each, but we don't know how many magazines? But is the cost of the magazines going to change if I bought 100 books? No, it would just be 100 plus 1M. How about if I bought 40 books? No, it would be $40 worth of books plus $1 per magazine. Okay? So this is more of a deductive reasoning kind of problem. It's just asking, does the cost of magazines affect the cost of the books? And the reason that it doesn't is because books and magazines are independent, right? Because the number of books that I buy doesn't affect how much the number of magazines costs. I'm going to go ahead and move on to number 4 here. All right, this has a lot to it. Let's write down the important information as we go. Okay, so let's see. Satellite cell phone coverage. Okay, satellite cell phone coverage bills on a monthly basis. Okay, so each bill includes $19.95 service fee. That's our service fee. Okay, for that gives us 500 minutes. All right, minutes. Okay, plus $9 and $3.95 of tax. And let's see, plus I'm just going to put this right here. It's 15 cents for minutes over 500. Okay. The following expression describes the cost of the cell phone per month. And it looks like we have everything set up here. The only thing that they did different is that they combined these two, because those two are just basics in the cost of the problem. So when they add those two together, they get 23.90 plus 0.15 M. Our last question. If satellite cell phone lowers its service fee, how will the expression change? So first we have to identify this was overage. I'm just going to erase that. So here is our expression here. And what it's asking is, well, what happens if this service change, the service fee, what happens when it changes? Triangle is change. You'll see that once you get to chemistry. All right, so in the chat, what do you think is going to happen to our expression here if the service fee, lowers? Go ahead and chat it. What do you think? What's going to happen to our service fee, right? Or how is the expression going to change if we lowered the service fee? Let's see. Looking in the chat, anybody? Okay. So that's enough time, probably. I see a couple pieces of input. So if the service fee changes, remember this 23.90 came from combining our service fee and our tax. So what I would say is, in this expression, the 23.90 amount will decrease as the service fee decreases. Okay? It's just explaining what we have come to understand here. All right? All right, I'll give you a moment to go ahead and look that over. Let's see, now we're looking at page... Oh, it's on the other side. Or we're looking on number, looks like 6 from the workbook. You know what? Let's see. Number 4. Okay, number 4 is very, very similar in the book. So I'm not going to do number 4. We only have 5 minutes. So I'd like to do number 6 in the book. All right, go ahead and screencast if you haven't copied that down. Or sorry, screenshot it. All right, let's see. What values of x allow us to have greater than 1? All right, so I say we plug in some values to see what happens. So you can make your function machine. And if it has to be greater than 1, I'm going to put, let's just put 1.1 because we'll use our calculator for this. That's going to be plugging in 0.05 times, raised to the power of 1.1, which is fine. We can put that in as a problem. I'm going to go ahead and put in 2 and 3 just to see what happens. All right. And let's see. Why did I put that? I don't know why. Those are my x. That's my y. I changed that. Everybody look right there. I changed that to x. So we're plugging in x values. We're going to evaluate it. Evaluate means plug in. Then we're going to get our y values on the other side. Okay. So I'll go ahead and use my calculator here. Now you don't have to write everything out here. You can follow along with this. Okay. Because all I'm doing is, look, this is actually important. You need to go 0.5, and then for this calculator, it has this button right here, where it's y to the x. You might also have a button that looks like that. It's a little chevron. That means exponent. So if I look at this, we have 0.5. We're raising it. And I have to do parentheses. Well, I don't have to, actually. 1.1. And that equals 0.466. So we'll go 0.4. Let's go ahead and just go 67. We'll round it like that. Okay. Now, just in our last minute or so here, I'm going to do this real quick. So we get 0.5 raised to the second, and we get 0.25. Then we go and do the same thing, 0.5 raised to the third, and that equals 0.125. So what is happening to these numbers? If you get confused, just think of it as money. So 46 cents, and then 25 cents, and then 12 cents. So look what happens. Let's see. We can rewrite this as that's not, as x increases, the y value decreases. Okay? That's all I'll say. That's fine. We proved it. We know. If you really wanted to, you could plug in like 1,000 here. If you plug in 1,000, it's going to be really, really, really small. Okay? All right, we have 1 minute left in class. So go ahead and first off, let me know thumbs up, sideways, down, what you got out of this session. Give it to me. Is it helpful to go over it? Okay, good, good, good. So just remember, we have all these times to check over homework as we go. Okay, so don't get too stressed on that. I'm going to go ahead and let you guys go ahead and go while I ring the bell. All right, and I'll see you Wednesday. Have a good day, guys. Take care. All right, see you guys.
I have a question.
Great. What's your question? Let's see. The following expression describes the cost of the cable service per month. And they are, let's see. It looks like what they did here is combine these, $34.75 plus $2.99, the number of movies. Okay, so that's what that is. Now looking at that, it's really just, okay, the service charge and the tax, that's this amount, plus, hey, every movie you buy above that, just like if you get cable and you want to get someone on pay-per-view, you're going to have to be looking at how much it costs and multiplying it by the number of movies you get. So looking at this, $34.75 plus $2.99 M. Now, what is the last question? If absolute cable lowers the service fee, how will the expression change? So they're saying, hey, if they lower this, if this lowers, right, what's going to happen? Now, looking at that, the service charge plus the tax equals this. So what in the expression is going to change? Is 2.99 times the movie's purchase going to change? No, because that has nothing to do with the service charge. So when I'm looking at this, I need to just kind of break it down, put it all here so I understand what each number is talking about. That's key, because otherwise we wouldn't be able to figure out that, you know, these two added to give us the $34.75. Now, if the service charge goes down, then I know that, let's see, the $34.75 will decrease when the service charge, service cost decreases. Okay, and that actually for this problem would be the answer. It's a matter of being able to understand what parts of the expression they're giving you is, and then if they change the service fee, it's going to change that value that's part of my final expression. Yeah? All right, if you asked for that, go ahead and give me a thumbs up, sideways, down. especially if you ask for that. But everybody, go ahead and give it to me. How do you guys feel about it? Feel pretty good? All right. So if you're not understanding it like late week, I still want you to go and not get discouraged, because we're going to keep on working. We have Monday to get over it. You have the videos to watch later if you need to. Okay? All right, we'll get it. All right. Let's see. That was workbook number 5. So let's go ahead and do